Okay, so trig functions. This is where this starts getting really cool because I think this is like a puzzle. If you don't like puzzles, I'm sorry, you're probably not gonna love this, but I think this is pretty neat. So we want to find the integral of the tangent of x. And so you quickly scan through your integral rules, and there is no rule for tangent of x. There's nothing that we know of that we take the derivative of that results in tangent of x. The derivative of tangent is secant squared. The derivative of secant is secant tangent, which is a product, so that's not going to be helpful. We can't like multiply by secant somewhere. So instead, what we need to do is get a little bit fancy with what we have going on. And in this instance, what we're going to do is use our trig identities to rewrite this. So I know that tangent is equal to sine of x over cosine of x. And now, again, we always want to be thinking of the lines when we see fractions now. I want to be looking at it and saying to myself, is the derivative of the denominator equal to the numerator? So we think, what's the derivative of cosine? The derivative of cosine is negative sine. So that would be really nice if I could get that to work. And I can, because what I'm going to do is I'm going to rewrite this integral to be exactly how I want it. I'm going to put this negative sign in here. But I can't just put a negative in there because now I turned it negative when it's not supposed to be. But if I also multiplied this by a -1, then that puts my whole thing back to positive and we're all within bounds. Okay? And so because I've done that, now I know that this is a case where I have u prime over u. And so this is going to be negative because of what's on the outside, natural log of the absolute value of the cosine of x plus c. That's the derivative of tangent of x. And that's not something that we would have seen otherwise, but the natural log, these natural log integrals really do a lot for us. To kind of open up doors to functions that we weren't able to integrate otherwise before. So I think that's kind of nifty. Let's look at the next example here. Okay, I'm going to work through this one, and I'm just going to warn you in advance. This example is kind of magical. It seems a little far out there, but this is where this formula for the integral of secant of x is going to come from. And you can probably hear in my voice, I'm excited because I think this is cool. But so secant of x, there's no derivative that gives us that, so there's no way that we can integrate just as it is. Here's what I do know though. I know that if I can get a secant squared, that is going to be useful because the integral of secant squared is going to be tangent. I also know if I could get a secant times tangent, that would be useful because that is going to be the integral, or that's the derivative of secant. So either one of those two things would be really helpful. We are only allowed to multiply by 1. And you can try all different forms, and I never would have come up with this one on my first try. Think about last year when you did, for the first time, you verified trig identities, how many times you had to start over and find another way that was going to be helpful. And it's the same idea here. It's almost like you're verifying a trig identity. You have to get it to some sort of form that is going to be useful to you. That's why we spend so much time in pre-calc manipulating those trig expressions. And so here's ultimately what we've come up with that we're going to do here. I'm going to take my integral of secant of x, and like I said, this is going to feel like some real math magic here. I'm going to multiply that by secant of x plus tangent of x over itself, because really, what is that? That is just 1. And again, we're allowed to multiply by 1 all day long. Alrighty. It may not feel quite like we've gotten anywhere yet, and hopefully you get an aha here in a second. But so I'm going to go ahead and distribute out that secant of x. And so I end up with secant squared of x plus secant x tangent x. And hopefully that is kind of maybe making some light bulbs go off there, because those are both of the forms that we just talked about. And that is over secant of x plus tangent of x dx. Now, if we can get this to the form of u prime over u, that would be excellent. So let's consider the derivative of secant of x tangent of x. If I take the derivative there, and this is really bad notation, but I'm going to write it like this. The derivative with respect to x is equal to, the derivative of secant of x is secant x tangent x plus the derivative of tangent of x, which is secant squared of x. And do you notice that if I just reverse that, that is what we have for our numerator. So that's pretty handy, because all that tells us then is that this is going to come out to the natural log of the absolute value of secant x plus tangent x plus c. That, I wish you guys could see my face right now because I'm so excited. That is wild that we were able to come up with that. And so, again, would I have gone straight to that? No, I absolutely did not. I tried first multiplying by like secant over secant. But then again, that left me a secant squared in the numerator, but the derivative of secant was not secant squared, so that was not helpful. I knew I needed to get a tangent in there somewhere, so I could multiply by tangent over tangent, but then I get tangent in the denominator, and again, not helpful. And so this is finally kind of where I landed, because that was going to get me the secant squared, and that was going to get me the secant tangent. That is some pretty high level good stuff right there. That is pretty cool. But luckily for you, we have gone and made this handy dandy little list for you of all of the integration rules for the trig function. So add these to the integration rules that you should know. This is the one that we just did right here. And so that's just kind of to show you where that came from and how we got that. And if you're feeling bored, maybe you could work through some of the rest of them. But those are the things that you need to know there. From here on out, we are working with some u substitution, some definite integrals, and things like that. So I'm going to go ahead and just post up the work for these next couple of examples, and you can hopefully just kind of copy them down and follow them along yourself, and then I'll come in and take questions over this tomorrow, but hopefully this is enough to get you started. So here is example 10. Here is how this works out. I would take just a second to copy that down, maybe put the video on pause, and then you can come back and listen to some of my comments here. But the thing that I want to point out, I've mentioned to you before that when it comes to your trig identities, the main things that you need to have memorized is all of your reciprocal rules. So like secant is 1 over cosine and things like that. You need to know your quotient rules. Tangent is sine over cosine, cotangent is cosine over sine, and you need to know your double angles, like sine of 2 theta is 2 sine theta cosine theta, and you need to know your Pythagoreans, and you need to know them in all forms, not just sine squared plus cosine squared equals 1. That is not the only one that you need, okay? So because this one, it's pretty hard to get anywhere if you don't recognize that trig identity that 1 plus tangent squared is equal to secant squared, okay? And so from there, it's just working through that derivative. This step here is just using that formula that we had just derived previously, and that formula off the list, And then you're just going to work through that the rest of the way. You can rationalize that at the end or not, doesn't matter. Remember, the natural log of 1 is 0. That's why that went away, and that's what we get. There's no plus c because this was a definite integral. So here is example 11, all worked out for you. Don't forget that average value you multiply by 1 over the width of your interval there. So from 0 to pi fourths, that's a distance of pi fourths. So 1 over pi fourths, which is 4 over pi, is what we multiply that integral by. Again, we're just using the rule here for the derivative, or I'm sorry, the integral of the tangent of x. That's one of the rules that we had also derived. And so from there, it's just crunching out the numbers and evaluating stuff. So those are how we can work through the trig functions. Once again, you can go straight to the formulas. You don't need to derive it if you're going to use it like we did in the last couple of examples here. So that is all that I have for you. I'll see you later.